So my estimate is that Jacquard similarity between set S1 and S3 is 1. All other pairs is going to be 0. So this is a pretty coarse estimate. It's either 1 or 0. Now Jacquard similarity was in the range 0 and 1, so it kind of makes sense. But you know, it's a pretty rough value here. So that means before I had 0, 1/6, 1/5, 1/4, 0, 2/5. Now my estimate, I'll just write it down in this column here in a different color, just so you can see it, was going to be 0, 1, 0, 0, 0, 0. Okay, so it's a pretty coarse estimate here. But, and so this is basically how it works, but the claim is that the expected value of Jacquard similarity between A and B is going to be equal to the true Jacquard similarity. So this process, which gives me a 0 or 1, is going to have the right expected value. So I'll come back and prove this at the end, given we don't get bogged down someplace else. It's not too hard to see. The proof is not too hard, so we'll put it off until the end of class, unless. So now I've done this. I've converted into this randomly permuted matrix. I've taken the highest labeled element that's in the set, and then I can get a value 0 or 1. Any value is going to be way off, right? The value should have been, say, 2/5. I'm at least going to be off by 2/5, so this seems pretty bad, right? But, so, in that first week of class where I was going through these randomized techniques, this actually fits the mold of something. We have some estimate we can get, which is in some bounded range, but between 0 and 1. In fact, it's only 0 or 1, and has the right expected value. So, what could we do to get a better estimate now? Don't worry about the computation yet. I'll kind of show how to do this a bit more efficiently.
With the expected values, right, could we just do it over and over again?
That's right, yeah. So we can repeat this a bunch of times with a bunch of different random permutations. And every time we're going to get a 0 or a 1, and then we're going to take the average of these. Right? So so then we're going to repeat this k times. So that means we're going to take k random permutations. So each maps from S, for me to set, say S1, to a vector now of M1 of S1, M2 of S1 to Mk of S1. Right, so each of these values, M1 to Mk, are going to be like these values here. They're going to point to one of the elements in the set. So I'm going to store one of these elements in the set. And so then if I want to compare two of these sets with each other, I'm going to estimate the Jacquard similarity by, say, A, B, by 1 over k times the sum of right? So I'm going to go and look whether these values are equal. If they're equal, I'm going to, this is writing down an indicator function. If this is true, I get a 1. If it's not true, I get a 0. That's this function here. I could instead write the Jaccard's, this approximate for a particular index, right? So I have all these values mi, each of these elements of this vector mi, I can compare them. If they're equal, I get a 1, and I average all these, right? The average is like getting the expected value. That means the more elements in the average, the closer this expected value is getting. Right? So if you use those Chernoff-Hofting bounds that I mentioned earlier in class, you can show that you can get within any value epsilon close with some number of these, with some number k of these permutations. So now, in order to get a really good bound, you need a lot of permutations, but this works, doing like 100 or so of these works pretty well in practice for looking at these, comparing these websites together. You don't need that small of an error necessarily to get a good estimate here. Especially if you do a good job of constructing your sets. Let me bring up this board. All right, so this is still a really slow process. So so how would I do this? So before I describe how to do this more efficiently, is it clear what's actually going on here? You have this. You're randomly permuting the order of these, and this gets you a single value as a single representative of it. And each of these representatives, whether they are the same or not, will have the right expected value, and then you can amplify this by repeating it. Okay. So, but this seems extremely wasteful. This is much slower than what we talked about before, where you could just keep them in sorted order and scan them once, right? So the good thing is that this representation of the set seems to be pretty small once I can get here, but this whole randomly permuting thing seems pretty slow. So how would I do something more efficient? So in fact, so this is called min-hashing. Okay, so the hashing part is the trick we're going to use. We're somehow going to use something like a hash function here. Okay, and so it's min-hashing. We only need to keep the smallest one. So this random permutation seems like a lot of work. What could we do instead of a random permutation? Or what can we do in order to calculate? We just want to get this value. We don't need all of this information here. It's mainly zeros, right? So we don't need to calculate all the zeros. We only need to calculate the smallest value for some permutation. Yeah?
You just have a random hash function, and you just keep the smallest hash value for that particular hash function.
That's right. Good. So we're going to have a hash function. So a hash function h, we'll call this hi. And so this will go from our set n, and let's say it goes back to n, right? Some other set. It could be something larger. In fact, typically, if the matrix is really sparse, having this being smaller than whatever n is going to be okay. Okay, so we're going to have this hash function. And so then our goal is to calculate this value m. So what we can do is for each I in our set, right? right? So we're going to do this on a set, and we only need to look at the elements in the set. So for each of the ith element in the set, so this can be like a value 2, right? So this is, what we do is we, so first we'll start with, we'll start with the value, let's call this x, and we'll call this min, and we'll set this to infinity to start with, or some maybe n plus 1. Okay, so now for each value I in the set, if h of I, use j here, is smaller or equal to our value min, then what we do is we set min equals to h of I, j. And so in fact, this value min at the end will end up being a representative that looks like this value mi. We don't actually need if our set is going to be one of these k-grams, we don't need to store the k-gram. We can just store a representative value of the hash function. So in fact, what I can do here, instead of using this value min, I can use this as mi of s. Starts out something large. If it's greater than mi of s, then I replace it. Okay, and so actually I want to create, for each of, I'm going to have a bunch of these hash functions, right? I'm going to create a vector here. So this is my representation, this vector. And if I want to create this whole vector, I don't want to have to actually scan over the whole data every time. So I could repeat this whole thing for each of the hash functions, but I don't want to have to read through this every time. So instead, I should have left a space in here. Let me rewrite this. So for I equals 1 to k, say if hi of s is less than mi of s, then set mi of s equals to hi. Okay. Right, so I just added this for loop in here. That way I don't have to read over these multiple times. This ends up being a little bit more efficient than putting this for loop outside. Okay, so now let's convince ourselves that this is going to give the right answer. Okay, so in order for this to work, I need a small assumption. I need that this hash function is not going to map any two elements in my set to the same location. If I do that, I'm going to get a collision, and I would elevate them both to the same value, or two elements in the two sets I'm comparing. There's some chance that'll happen. You may be able to choose this hash function so it's a perfect permutation. That turns out to be a little bit harder to do. If this output range is large enough, then the chances of a collision is going to be pretty small, right? So if this is much bigger than 2 square root n, then the chance of a collision is going to be pretty small here, or 2 square root n, where 2 square root t, where t is the total number of things in both the sets you're comparing. Then the chance of a collision is going to be pretty small. Okay, but otherwise, what's happening here is you're going to go through this for loop. For every element, you're going to check its hash value, and it's going to give you the ordering here, the number of the row it's on. So if I go through, let's say I do this for set number 3, 2, 3, 4, 6. Let's not do that. Let's do set 4. So the first value for set 4 I'm going to get is 1. right? And this will give me a rank of 4. So my M1 value will be 4. Then I'm going to do it for the value 4. That will hash to the order 5 in this permutation. That's larger than the M1, the MI value that I have. So I don't update anything. Then I do it for 6, and I get a value of 3, and that's going to be smaller than before. So 3 was, I'm going to have the rank 3. So here I stored the element, but 6 was the third thing in the permutation. So that's just as good to store. So do you believe that this function, this hash value at the end, this vector at the m will be equivalent, assuming my hash functions work well enough, to this value here? Is this clear? Is this the kind of different things I'm doing here? This one is going through this matrix representation. And this one kind of skips the whole thing. I can just go through these 4 loops here. Okay. All right, so let's see how fast does this algorithm work? Okay, so let's say that my domain n is of size n. I'm going to use k hash functions. Okay, and I'm going to have n sets. Okay, and let's say let's say that t is going to be the total size of all sets. So t is going to be equal to the sum I of, so the size of all these sets. So if I do this for one set, so if I do this for one set, how long is this algorithm going to take? I have to go through, for each element of the set, I have to run through k hash functions, and this basically takes constant time, right? So for one set, this is going to take O of s times k time. All right, so who has not seen this on this big O notation before? All right, just a quick review. This is very common computer science notation for the asymptotic running time. So you're trying to ignore constants. You're trying to see how something scales as the elements of your size of your problem grows. So there's this if statement and this assignment takes some amount of time that depends on some constants which are particular to the computer I'm running it on, right? But if I run this algorithm on any computer, as the size of the set grows or as the number k grows, it's going to grow with this order. So this is a big O of the size of s times k. And so that way I know as these parameters grow, this is how I can compare algorithms kind of in the limit, where I can ignore kind of the hardware details. And so this is very common in computer science, and you can, it's very useful. It measures the worst case running time, and you can, so you can, if there was another term that was, if it was like O of s times k plus k, I can throw the k part, the plus k part away, because that's not dominating, that's not the dominant term. So I'll mainly, in this class, avoid using this notation, and I don't think you'll need it for, if there are homework questions that ask for it too much, if you give things without the big O, or it's close enough, it should be okay. I'll pretty much avoid using it, which I think is generally a feat for kind of a class with this many algorithms in it. But this scales with, for each set, the size of the set times k. So then if the total size of all the sets is t, if I need to run this pre-processing for all the sets, then the total size, the total time for pre-processing is going to be O of t times k. Right? So this is the size of my input, t, and I have this k term here. So k is going to depend on the amount of air I want. So k will be basically 1 over epsilon squared, where epsilon is the air I get I get in the Jaccard distance estimate. So that means it's going to be independent of this domain size n here. You're going to have a huge domain size. I don't need to look at this in order to compare. Okay, so this is pre-processing. If I want to now compare two vectors, I have these two vectors, both of size k. How fast does it take to compare them to get this estimate? So to compare, let's call this vector m of s equals 2 of s. Okay, so this is a vector m of s, big M of s1, and I have the same for s2. So I want to compare. I want to compare m of s1 and m of s2. Comparing them is only going to take O of k time. So now this is independent of the size of any of the sets, independent of the whole domain. It only depends on the number of hash functions I need. Okay, so I can now compare them in time that doesn't depend on the size of the original data set. And by making k larger, I'm going to get more accurate estimates. So in your next homework, you're actually going to implement this algorithm. So hopefully you're paying attention. So it's pretty simple, right? Once you get the hash function working, which hopefully you got some version of a hash function working for this homework, which is due on Wednesday, then you'll be able to do something similar to use a hash function here. And then it's a matter of some for loops. Right? So I can now compare them very quickly, and using something like k equals 100 will work pretty well, independent of the size of n. Okay, so anything else I wanted to say? All right, so the other thing is the space I need for any of the sets is now also only O of k. I can throw away this representation of the sets, right? I may have come up with these very elaborate different ways of getting these k-grams. Maybe I threw other information in there in the sets that are similar. But I can throw all that away. I only need to keep this vector representation of it, this 0, 1 vector. So this is not numbers. So this is just going to be a set of these k different numbers. That's going to be my full representation of whatever objects I started with. Start from documents, start from whatever. Now I have k numbers in a vector I can compare.
So this will mean that irrespective of whatever your sets are, it's going to give some value. I mean, how does this depend on what the sets have? Because you're just using some hash function.
Right. So if this domain size I'm mapping to is large enough, I don't need it to be a perfect permutation. I just need the ordering of the top element to be preserved. If there's a collision that's not the highest ranked element, it doesn't actually matter, right? So, if this is a large enough value, then it's essentially going to give me the minimum value of the permutation. Is that the question? Or
My question is, since you're just hashing to some random values,
yeah.
okay, how does it really reflect the problem of getting intersection between sets? Because it's not containing any values from the sets now.
Right, so I've got some time, so maybe I'll try and prove this, and this will shed some light on why this is calculating the intersection. In fact, it's not really estimating the intersection so much as it's estimating the Jacquard distance, which has to do with the intersection divided by the union, and that's what estimates.
What I'm saying is, if there was same number of values in those sets, like 6, okay, and the sets were somewhat different, would it compute the same kind of values again?
So if the sets are very different,
Yes.
right, then the estimate will probably, so that means the Jacquard distance may be 0 or close to 0. Right, so let's say I look at sets 2 and 4, right, or the sets 2 and 4, which have a Jacquard similarity of 0.
Yes.
Right, so anything I hash, if I look at 1, 3, 4, 6, those are the only elements that I care about. That's either in set 4 or set 2, right? One of those is going to be the highest in the permutation order. In this case, the highest is going to be 6, right? If this is the highest, if this is in set 4, then this is going to be the m value for that set 4, and set 2 is going to have m value corresponding with 3, which is much lower. They're not going to be the same. They can't be the same because they can't have the same highest ranked, the minimum value of the hash. So they have to be. So it's going to preserve this difference. So that's really what this result is saying, that the estimate is going to have the right expected value. You can only have this one here if things happen to align, and if that's a small probability of happening to align, your estimate is going to reflect that. All right, so let's try and prove. Let's try and prove this property, and hopefully this will give some light into why this works. So we'll try and prove that the expected value of Jacquard similarity hat, or estimate, is going to be equal to the true Jacquard similarity. Okay, so there are only going to be three types of elements that we care about. Okay, so type X are going to be when, so if you look at this table again, we'll start with this randomly permuting table. So we're going to types of these rows, right? So 3 types of rows. So both A and B have a 1. Okay? Type Y is either A or B have 1, but not both. Okay? And then type Z, both A and B have 0. Okay, so let's look at this example again. So if I do this for, let's do this for rows 1 and 2. This is going to be a type X. Okay, so 1 and 2 is a bad example. Let me do 1 and 4. Okay, so it is. So this will be a type Y. We'll do this for the Jacquard similarity between S1 and S4. Thanks. So this is the type Y because this one has a 1 and this one is a 0. So one of the sets has a 1, but not both. Okay, so this is also a type Y. This is also a type Y because now this one has a 1, but this one does not. Finally, row 1, this is a type X. And also for 4, this is a type Y again. And then row 3 is a type Z. Okay, so in general, in most of these cases, most of the rows will be type Z. Most of them, so these we can completely, these are going to be completely, so we can completely ignore these rows, it turns out, right? So now, if I were to use these types, and I said that these were actually sets of rows, then the Jacquard similarity between A and B is going to be the size of type X over the size of type X plus the size of type Y. Right, so this is going to be the union of all the rows that have a 1 from either of the sets. And this is a union from the rows that have 1 in both the sets. Right, so this includes, each row corresponds with an element, so this is the union. So this is equal to A intersection B over A union B, right? By looking at these different types. Okay. So now, let's look at the probability that this value is equal to a 1. So the probability that it's equal to 1 is actually going to be the same as the expected value because the value is either a 1 or a 0. Okay, so the probability that this A, B is equal to 1, so this is going to be the same as the expected value here. So it's not going to depend at all on the rows of type Z. If those end up being the highest ranked row, it doesn't matter because neither of them will register as the minimum value, as this MI value. Right? So the probability it's a 1 is the probability is looking at, out of all the rows that are TZ or TY, which one of those becomes the minimum in the order. Right? So if it's a TY row, it gets a 0 because only one of them has a 1 in that case. If it's a TX row, it's a 1. Right? So that probability becomes this number of TX rows over only the TX rows and the TY rows. So I only consider each of the TX rows or the TY rows has a chance of being the minimum, and they're all equally likely. So I look at just these rows, and only if a TX row, where they both have a 1, is the minimum row, does my estimator equal 1. And so this is exactly the Jacquard similarity. So then the probability to 1 is the expected value, right? The expected value of this. Right, so this is equal to 1, which is the value it gets times the probability that equals 1 plus 0 times the probability that Jacquard similarity is not equal to 1. Right, so and it doesn't matter what this is. I just need to look at this probability times 1. So I get exactly, so the expected value is equal to this, which is exactly the Jacquard similarity. So does that make sense? And the real fascinating thing about this, so this was used in a lot of the early search engines. I'm not sure it's still used in Google or not. There's a lot of black box stuff they don't tell you about. But this really works well because this does not depend at all on these TZ rows. The rows that have zeros in both of them. Right, so does this help explain your question of, it doesn't matter what's in the sets, this hash functions, this min hashing process is preserving this probability.
I'll have to think more.
What?
I'll have to think more.
Okay.
Maybe I'm wrong something.
Yeah. So if this went a little fast, I spelled it out in the notes, so you can go through and it's basically the same argument, but you can go through a little bit more slowly. But okay, so there's still a problem with this that we haven't solved yet. We can now do this pre-processing, which is pretty fast. It's basically the time it takes to scan over and create these k-grams. In fact, instead of keeping them in a set, every time I create a new k-gram, I can pass it through my hash function. Even if I passed the same one before, I can compare it to there. So I just have a factor k on top of whatever time it took to create all these k-grams. And I don't even need to determine if they're in a set. I just need to keep the minimum from each of these as representative and do this k times. So these representatives, these vectors that I'm creating by representatives, did not take that much longer to do. And now I can check if two of them are close in O of k time, which is going to be pretty fast, much faster than scanning through the documents. But typically what I want to do is I'm going to have a large set of these documents. Think of, I'm Google, I've scanned over the entire web, or almost all the web, and I've got a representative, and maybe for Google they have something larger than 100 numbers, they may have a bigger space, but they have a representative for each of these web pages. So now I want to know, are any of the web pages close? Do any of them have a high similarity? And if any of them have a high similarity, it's probably a duplicate. I've seen this before. And I don't want to rank them both really high. Right? So I don't want to go and check every single one of them in O of k time. I want to do something faster than that.